Hi, I'm Jack Dongera from the University of Tennessee. I was the 2021 ACM Alan Turing Award recipient. And today I'd like to talk about high performance computing and where we are today and perhaps looking into the future. Traditionally, science and engineering has been done using theory and experimentation. Theory is a paper and pencil calculation that we do to carry out some ideas. Experiments take those theories and try to put them into practice. Experimentation could lead to modifications in the theory, and then the theory would be put back into experiments. Today, sometimes it's too hard to construct a physical experiment. Think about building a large wind tunnel. Perhaps that's too expensive to do, or think about looking at two galaxies colliding. That's an experiment that we really can't perform in a laboratory. We have to carry it out using simulation. So simulation has been called the third pillar of science, helping theory and experimentation with computational experiments. And we think about doing those simulations and computational experiments on high performance computers or supercomputers using numerical methods that obey the physical laws. So a typical supercomputer today starts out with a chip as the basic building block. We take that chip, a computer chip with multiple cores, and we think about putting it on a board. So we put multiple chips on a board, and sometimes we augment those chips with accelerators. And the accelerators we use typically are graphical computer processors, GPUs. So the GPUs boost the floating point capability of the CPU to give us more computational power. And then we take those boards and we put them into a rack or a cabinet. We fill up the cabinet and think about connecting it together with some kind of a network so we can pass information from one part of the machine to another. And then we take that cabinet and fill up a room, replicating it to fill up a room, connecting together those cabinets with some kind of interconnect so they share information, and we call that a supercomputer. That's typically how supercomputers are built. One of the largest ones is at Oak Ridge National Lab. It's called Frontier. It occupies roughly the footprint of 2 tennis courts, if you will, and consumes a tremendous amount of power when it's running. So the environment for high performance computing today is highly parallel. It's distributed memory. We use MPI as a programming mechanism, the message passing interface for sending and receiving informations from various parts of the machine. We also use a programming model called OpenMP for dealing with parallelism on a node itself. As I mentioned, the machine at Oak Ridge is one of the fastest machines. Its peak performance is at 2 exaflops. And I'll tell you what an exaflop is in a moment. And that machine at Oak Ridge has about 8.8 million cores in it. So it's composed of 9,408 nodes. It consumes 30 megawatts of power. And if you think about a megawatt, you should think of here in the US, if I use in my house 1 megawatt over 1 year period of time, I'll get a bill for $1 million. So it's very expensive to run these machines. And the machine at Oak Ridge is composed of a CPU from the AMD company, along with 4 GPUs. So that makes up one of those 9,408 nodes. Those GPUs, again, are used to accelerate the performance. And 98% of the performance of the supercomputer comes from the GPUs. So the CPUs itself contribute very little to the performance. The computing environment that we have is heterogeneous, usually with commodity processors, with commodity GPUs. Communication between various parts of the machine are very expensive, and we have to be aware of that when we do our computations to minimize the communication costs. And today, we have different floating point computing performance or accuracies. We typically think of scientific computing being done with 64-bit floating point precision, and that sometimes is augmented with 32-bit floating point precision. But with the arrival of machine learning and artificial intelligence, those applications can get by with a lot less precision. So we have hardware today which does 16-bit floating point and even 8-bit floating point arithmetic. And we, of course, can get performance benefits if we use the lower precision And we should be thinking about if we can get away with, if the computation allows for less precision throughout the computation, or maybe use it selectively during the computation. So the fastest computer is at an exaflop. So what is an exaflop? Well, first, what's a flop? A floating point operation is an add or a multiply of 64-bit floating point numbers. That's usually what I refer to as a floating point operation, or a flop. And an exaflop is a billion of those floating point operations per second, or 10 to the 18 floating point operations per second. So that's the rate at which that we're going to be processing things. And you should think about an exaflop. If we had the whole world's population and we had each person do one calculation a second, it would take 4 years to do what that exaflop computer can do in just 1 second. So that's sort of the power that's there with that computer. A number of years ago, I started out by writing a benchmark. So I became an accidental benchmarker, in the sense that we were constructing a software package called LinPack. It's a package of software for solving systems of linear equations. And in that user's guide for LinPack, I constructed a benchmark for solving a matrix of size 100. And I did that and timed the results and computed the execution rate. And from 1979, when that first benchmark report was published in the appendix to the LinPack user's guide, I've been collecting information. And that first one had computers ranging from a Cray 1 down to a DEC PDP-10. And the list looks something like this, where the computers were ranked or rated based on the time it took to solve the problem. We converted that to a floating point execution rate. And the fastest computer, when this was done back in 1977, was a Cray 1 at the National Center for Atmospheric Research, and it ran at 14 megaflops. So that was the peak performance that they were able to achieve on that computer for the benchmark. That benchmark has gone through a lot of changes and improvements. Hans Moyer from Germany and Erich Strohmeyer had a list of the fastest computers. I had a benchmark which actually ran something on the computers. So we decided to put our two lists together, and that was called the Top 500. So we have a list of the 500 fastest computers in the world. That list comes out twice a year, and it ranks the computers based on solving that simple problem, solving a system of linear equations where the matrix A is dense. I give you the matrix, I give you the right-hand side B. I ask you to solve that problem using Gaussian elimination with partial pivoting. When you solve that problem, we look at the time and we convert that time into an execution rate. And we do this for 64-bit operations. So we've been doing this. The list comes out twice a year, and it usually comes out in November and June. And the current list, of course, is from June of 2022. So this is a snapshot, if you will, of high performance computing over time. We're looking at here, the red dots are charting the fastest computer. So here in 2022, the fastest computer is at 1 exaflop, 1.1 exaflops. The slowest computer on the list at position number 500 are represented by these orange dots, and that's at 1.65 petaflops. And the blue line here is charting the sum of the 500 computers, or about 4.4 exaflops. And you can run this benchmark on any computer. When I run it on my laptop, I have an Apple Mac laptop. When I run it on it, I get 166 gigaflops. So 166 gigaflops is the performance for solving that benchmark problem. And when we look back, my laptop was actually faster than the #1 computer back in 1993. So the #1 computer back in 1993 was a thinking machine, CM5, with 1,000 processors. It was used at Los Alamos National Laboratory for doing nuclear weapons design. When I have a laptop, which I really use for email or giving talks, being faster than that machine, that was the most powerful computer back in 1993. This is a list of the top 10 computers today. It comes from the June list. And you see that the #1 computer is this machine at Oak Ridge National Laboratory. It's called Frontier. It's integrated by a company called HPE. It has AMD processors and an AMD accelerator. It has an interconnect made by Cray. It has 7.7 million cores in it. So those are the processing units that were used to run the benchmark. It achieved 1.1 exaflops, and that's 55% of the theoretical peak performance. So the theoretical peak is a paper and pencil calculation. What's the cycle time? How many operations can you do per cycle? And that gives you the theoretical peak. So we're leaving a lot of performance on the floor. We're only achieving just a little over half of the performance for this benchmark. And it used 21 megawatts of power to run the benchmark. So again, to turn the machine on is a very expensive operation. And we could see that the US has 5 machines on the top 10. China has 2 machines, the Sunway Tahoe Light system, as well as the Tianhe 2A system. The Sunway uses a processor that was designed in China. The Tianhe 2A uses an Intel processor plus an accelerator that was designed in China. And all of those machines have custom interconnects. The Chinese were designed in China. And then we have a machine from Japan, very impressive machine called Fugaku, very impressive performance. A machine in Finland and a machine in France round out the top 10 systems on the list. Just want to point out the fastest machine here. This is the machine at Oak Ridge. It has a theoretical peak performance of 2 exaflops. It uses AMD processors. It has 9,408 nodes. If we take a look at this machine in more detail, what we see is that it has a theoretical peak performance if we use 16-bit floating point operations of 11 exaflops. So using shorter precision gets you a lot faster performance. We see that 99% of the performance is coming from the accelerators. So if you're doing computing on this computer, you had better be using those accelerators. Otherwise, you won't be seeing anything near the theoretical peak performance. And this machine has 37,000 of those accelerators on it. And sometimes it's a challenge to use those accelerators engaged in performance. So summary of highlights from the top 10 list, or from the June list of the top 500. Frontier is the #1 system. That one machine has 25% of the sum of the whole top 500 machines. It's achieved over an exaflop. Using 16-bit arithmetic, we can get 6.8 exaflops out of it. There's another benchmark that we have which uses 16-bit floating point operations. And when we run that, we get that 6.8 exaflop rate. The top 10 machines has 3 new machines, the Oak Ridge machine, a machine in Finland, and a machine in France. And those 10 machines, those top 10 machines, really are over half of the performance of the 500 machines. So you see it's very top heavy in terms of the top 10 machines really dominating the rest of the list. The entry level is at 1.52 petaflops, and China is the top consumer and producer of supercomputing when we look at that top 500 list. I'll have more to say about that in a moment. And Intel processors have the largest share. So we look at the processors that are inside of the top 500 machines, and we see that Intel has 78% of those 500 machines, and AMD has another 19%. So that architecture, the x86 architecture that's in Intel and AMD, really dominates the top 500 list with 97% of the supercomputers. So looking at the number of supercomputers in various countries, China has the most with 173 supercomputers. US is second with 128, and then Japan, Germany, France, et cetera, rounds out the list. But China is not only consumes the most supercomputers with 173, they make the most supercomputers. So when we look at who's the producer who makes the most supercomputers, it turns out to be China in companies like Inspur, Sugen, and Lenovo. Those are the 3 main companies in China that are manufacturers of supercomputers. There are rumors that there are 2 exascale computers in China. There's one in Guangdong. It's called the Ocean Light. It's a processor that is produced by Sunway. It's a Chinese processor. And the reports or rumors that we have is that it ran over an exaflop, but they haven't submitted the results to the benchmark. But we know the machine exists. They've written scientific papers that were performed doing research on the machine. In fact, they won a very prestigious award called the Gordon Bell Prize in 2001 based on a computation from that Ocean Light system. There's another machine in Tianjin, the Tianhe 3, and that machine uses a Chinese processor and a Chinese accelerator. And there we think it's a little over an exaflop as well in terms of the performance on the benchmark. But those results haven't been submitted officially to the top 500 list. It's easy to do, but they just haven't submitted the results yet. So we see the performance improvements. Back here in 1997, we had the first petascale machine, terascale machine. Back in 2008, we had the first petascale machine. So roughly 11 years elapsed. We had 3 orders of magnitude improvement in performance. And today, going from peta to exascale, it took us 14 years to get to the next level of performance, another 3 orders of magnitude, and that was achieved this year. So you wonder what's going to happen in the future, how long it'll take to get to the next 3 orders of magnitude, zettascale. I would guess it would be more than 14 years, but time will tell. We have another benchmark called HPCG, and that benchmark follows on from the LINPACK benchmark. LINPACK benchmark was designed in the late 70s, and at that time, in the late 70s, floating point performance was very expensive. Today, floating point performance is not expensive, and that benchmark that was done in 1997 does basically a matrix multiply, where you do a lot of floating point operations. Today, our supercomputers are a little bit used for different purposes. They're used to solve 3-dimensional partial differential equations, and those problems are not based on matrix multiply. They're based on a sparse matrix vector multiplication. So we designed a new benchmark called HPCG, which does that kind of operation. It imitates more the kind of operations that are done in solving 3-dimensional partial differential equations. And this is a list of the top 10 from that benchmark. The Frontier system, they haven't had time to run the benchmark on that machine. We expect them to do that in the future. But today, the #1 machine is the Japanese machine called Fugaku. It achieved 16 petaflops on this benchmark, and that was 3% of the theoretical peak performance. So you see this benchmark here really showing a different level of performance. So if you scan down the list here, we see very little performance compared to the LINPACK benchmark or HPL benchmark. So you compare those two and you see the great difference between doing matrix multiply and doing a sparse matrix vector operation, the kind of thing we really use our supercomputers to do today. And we see this very small fraction of the theoretical peak performance that we're achieving on these computers. So there's a lot of room here for improvement, I would say, in terms of algorithms and software that can effectively use the machines. Perhaps another way to say that is the machines we have today are not really designed to do this kind of computation, to do a sparse matrix vector computation, the kind of thing that we need to solve large-scale 3-dimensional partial differential equations. So if we take a look at these benchmarks, the peak performance is listed here. We have the ranking according to different machines on the x-axis, and the y-axis is giving us the performance. The black dots are the theoretical peak. The green dots are representing the LINPACK performance, and the blue dots are showing the performance for this new benchmark, HPCG. We see this large gap in terms of performance, and the performance we achieve on a real problem is going to be perhaps somewhere in between, most likely closer to those blue dots, however, for the HPCG benchmarks. So recently we've seen artificial intelligence and machine learning take off. Artificial and machine learning have been around for a long time as research efforts. And why has that become so important now? Well, today we have a flood of data, especially using the internet. We can collect data that can be used for training our machine learning processing. We have this additional computing power that we have based on these accelerators or GPUs that we use. We have growing progress that's been made in the algorithms and theory that's led by research in machine learning and artificial intelligence. And we have this increasing support from industry building special hardware to effectively solve this problem. So machine learning can be used in many applications. It really enhances our ability to do scientific discovery. Machine learning is part of the computational infrastructure. It allows us to improve performance, and machine learning is really being pushed out to the edge where we're collecting data. We can use machine learning to help reduce and manage the volume of data that's collected from those edge devices and pushing it forward onto the computing platforms. So machine learning and computational science, we see more and more of it. We see it in climate studies and biology and drug discovery, in materials, and in high energy physics and cosmology. So it has many, many applications. It's going to be used more. It's a very valuable tool that computational scientists will use. Artificial intelligence, of course, is a broad area. It encompasses many ideas and concepts. Machine learning is one of them. Natural language processing, expert systems, vision, speech, planning, and robotics all fit under this large umbrella of artificial intelligence. And for doing machine learning, for looking at deep neural networks, the basic operation that we're doing is a matrix multiply. So our accelerators are well designed to help with that. And many of these machine learning applications can get by with very short precision, 16-bit floating point arithmetic in their computation. And we see many hardware vendors coming up with solutions to help with this problem. So the future, how will the future look for high performance computing? Well, we know that we'll have CPUs and GPUs. That's the current way things have been put together. But I foresee that we'll add on to that list. Not only will we have a GPU, but we may have machine learning devices, maybe having neuromorphic systems added onto the list, quantum-based computing, optical computing perhaps included into the mix to help solve computational problems. And future systems may be composed of many of these parts, and you may be, as a user, be able to dial up to be able to add into your configuration different components depending on the kinds of applications that you have for your particular mix of jobs. So the takeaway message here is that high performance computing is constantly changing. We started out with scalars, we had vector computing, we had distributed computing, we have accelerated computing today. We use mixed precision to help with those computations. We see really three computer revolutions that have gone on. One is in high performance computing, another in deep learning, and the third with edge or AI computing. Algorithms and software really follow the hardware in some sense. I think of hardware people throwing a piece of equipment over the fence, and the algorithms people and the software people have to scramble to figure out how to use that computer, and they spend the next 2 or 3 years doing that. So as a riff off of Feynman, there's plenty of room at the bottom. Let me say that there's plenty of room at the top, and that top we can exploit it through improvements in software, improvements in algorithms, and also using that hardware to help with that. In fact, there was a paper published on this concept. Charles Leiserson published a paper in Science back in 2020 with exactly that title. There's plenty of room at the top for what will drive computer performance after Moore's law. So thank you so much for your attention. I'm sorry I can't be there with you today. If you have any questions, please send me a question. I'd be happy to answer it. Bye for now.